3.5 waves homework. So let's have a look at the first question. It says, write down the wavelength of the wave. Well, the wavelength is one complete cycle. So if you start at 0, it goes up, and then it comes down, and then back up. So that's one wavelength. So it says 4 meters, because its distance is meters. You could even do, if you wanted to go from peak to peak, you can see 5 minus 1 there. It's going to be 4. And if you want to start here, one whole wavelength, 6 minus 2. So just remember, a wavelength doesn't have to be from peak to peak or trough to trough. It's just one complete cycle, and then it starts again. Write down the amplitude of the wave. Well, the displacement here is in centimeters, and it goes up to 50 centimeters. So the displacement's 50. If the wave travels with a speed of 2.8 meters per second along a surface, use the equation frequency equals wave speed over wavelength to calculate the frequency. So we know, oh look, I don't know why I've done an S there. That's really naughty of me. That should be a V. That should be a V. Let's change that to a V there. So that should be a V over F and lambda. So this fella here is your wavelength. This should be the wave speed. Wave speed's measured in velocity, because velocity is a vector and it's got a direction, so it's going to be going in a certain direction. So it's exactly the same as speed, though. It's still meters per second. It's just we use a V for velocity, and then speed was just a scalar, we call it. So there's my calculations there. I've found out what I've got. Frequency is what I need, and I plug it all in, and I get to 0.7 hertz. Use the equation distance equals speed times time, and all of these are given to you anyway. There's your speed, distance, time. There's your speed. There's your wave speed equals wavelength times frequency there. So that's because it's a foundation question. They're just giving it to you here, which is why it's only worth 2 marks. And it says there it wants you to calculate the distance travelled by the wave. So you get that the speed, which is given to us there, 2.8, and then the time then is 100 seconds. And then I've plugged all that in, and I've got a distance of 280 meters when I do it all. Okay. This next question then. Waves can travel across the surface of the mortar. Their speed depends upon the depth of the water. Water is placed into a plastic tray. The depth of water is measured. So this is one of our practicals we'll be doing, whereby we're counting the number of waves, and it'll depend on the depth of the water. Some people's time how long it takes the wave to travel 4 lengths. So the reason why they do 4 lengths is because it'll be hard to time one wave going 1 length, so they take that 4 lengths then, but they remember that that's 4 lengths, and we're going to have to remember that coming down here now. They repeat the timings for each depth of water, and here's the results. So let's just look at what's going on. The depth of the water there, from 0 to 3, that's our independent, and then we've got some trials there, time taken 1, time taken 2, and then they've done an average, and then sorry, and then they've actually used the wave equation where they can calculate the speed of that wave then. So complete the table to show the missing values. So that's just looking for a mean. Well, I got 1.4 plus 1.2 over, because there's 2 results, and that's your mean, 1.3. And there's bound to be more. Yeah, and then we're going to graph it. So on there you can see for 3 marks now, I need to come up with my scale and the plots. So when you look at it's giving you the axes, so it's telling you they want wave speed on a side and they want the depth of the water on the bottom. But we know that this is always going to be at the bottom anyway, the independent. So my biggest number was 3 there, and then my biggest number was 69 on this side. So it fits nicely. It's very rare will they give you something really hard. It'll always fit nicely, and this goes up in 0.5s there. So I've plotted my graph. It's a nice little curve. So as x increases, y increases at a decreasing rate. It's starting to trail off. How do I know it's decreasing rate? Well, for every box here, it starts and it goes up to 3, and then for another box, it's not so much 3 then. You know, there would be 6 if if it was even, it starts to level off. So for every box I go across, it goes up less, or not as high. I shouldn't say less high, but it's pretty much just leveling out. So it's at a decreasing rate there. Oh, and then I've said it there, as depth of water increases, the wave speed increases at a decreasing rate. So as one increases, the other one increases at a decreasing rate. Use a graph to find the wave speed of the water at a depth of 2.5. Well, I've taken a line up there, and then at 2.5, I interpolate, and it comes back to there, which was 66, because every square is worth 1. So 66 there. I don't know what this line was. I think that was a mistake there. So not to worry. Not to have you panicking. And then use data from the table and an equation from page 2. Now this is the important bit, from the table, not the graph. So read the question. Use data from the table and the equation from page 2 to calculate the length of the plastic tray. Now, remember it was 4 times that it went. So the length of the plastic tray. So if we just look, I'm going to take values from the table. So to get the length of the plastic tray, I'm going to do distance equals speed times time. And I've just taken any value here. So if the wave speed is 30 and the time is 3 seconds, the mean time, then I can get my distance from that. And it'll work for every one of these. So I've just picked the 30 and the 3. And then that's going to get you 90 meters. But remember now, it does 4 lengths. So I need to divide 4 into that. So 90 divided by 4 is going to give me 22.5. Because 90 meters is what it travels in total. So back, 4, 4 times. So that's what it travels, 90 meters. But what's the length of the tray? Well, I'm just going to divide 90 by 4 to get me 22.5 centimeters. And that's an average size for a tray. I can confirm. Next question. Infrared radio waves and microwaves are types of electromagnetic radiation, and they're used in long-distance communication. Complete the table below by selecting one of these, infrared, radio waves, or microwave. For optical fiber signals, well, that's going to be infrared. Satellite communications, always microwave, and signals for a mobile phone is also microwave. Which is why if you spend too long on your mobile phone, your ear starts warming up, because the microwaves are actually warming up your molecules of water in your ear. Which of the 3 types of radiation given above has the longest wavelength? Well, that is going to be... Which are they given above? Has it given radio waves? Given? Oh, yeah, there it is. Sorry. Yeah, so it is radio waves is going to have the longest wavelength, even though it's none of our answers. It starts red Martians invade Venus using X-ray guns. Next question. The electromagnetic spectrum is the name given to a family of waves. It includes light, infrared, and ultraviolet. All members of the family can travel through a vacuum. Okay, I'm just going to skip to the question. What is it saying? Name one part of the electromagnetic spectrum that is not mentioned. Okay, so I need to go back up and read. Well, it says light, infrared, ultraviolet, radio waves, gamma rays. So it's either X-rays or microwaves that are not being mentioned. Name one part of the electromagnetic spectrum that has a frequency greater than visible light. Well, red Martians invade Venus using X-ray guns. So UV, X-ray, or gamma. Give one reason why radio waves have a longer wavelength than gamma. It's because there's less energy transferred. Okay, they all move at the same speed, but radio waves transfer less energy because they're lower frequency. Lower frequency's got that relationship as if you've got a low frequency, you're gonna have a long wavelength. If you've got a short wavelength, you're gonna have a high frequency. Because frequency is the number of waves to pass a particular point each second.